Hello.
Hi.
Thank you for being with us today.
You're welcome.
Can you please tell us about yourself?
Yes, my name is Frankie Rupavar. I am the co-founder of the company Batteroo with the product Batteriser. I have been in the high-tech industry for about 30 years. I started in the early 80s. At the beginning of the 90s, I co-founded a company called Micron Quantum Devices, which ultimately was bought by Micron Technology. And the products that we brought was the non-volatile memories, which generated billions of dollars worth of revenue for the company. I was there as general manager and the vice president. I then joined a startup called Skyera in the area of storage. After 2.5 years, I was the CEO of the company, and I was able to successfully sell the company to Western Digital. Today, I'm helping my brother with the Batteriser.
You're the holder of over 500 patents. How can anyone have that many patents? Can you please elaborate on it?
Sure. I am blessed with a brain that tends to look at things in a different angle. I tend to be an outside-the-box thinker, and curiosity is really behind the whole thing. So I tend to look at things and try to come up with different solutions, and that's helped me over the years to come up with this many patents.
Do you have any more patents?
I think we have about 200 more patents that are in the pipeline trying to be issued, so they will issue at some point.
Can you tell us about your latest invention, Batteriser?
Yes, a significant number of batteries that are thrown away have as much as 80% of the energy still in them. Batteriser is a macro-thin sleeve that sits on top of the battery and helps extract that unused energy that's usually thrown away with the battery.
There has been few questions and concerns in regards to how this technology actually works. Can you please explain to us and everyone out there who has a few questions about the validity of this technology?
As you've heard, if it's too good to be true, it usually isn't. But in some cases, it is. And this is one of those cases. With every claim, a big claim, there's always people that doubt it and question it, which is natural. I fully appreciate the questions that they're asking, and we fully understand the question. And I will go into the details through both simulations and modeling, as well as the data from the actual devices. And we'll do a side-by-side comparison and show that it actually works. So the main gist of the question that's been asked from us, which is questioning the validity of this entire Batteriser concept, is the following. If you look at a curve of time versus voltage of a battery with a constant current, let's say 100 milliamp, you will get a curve like this. A lot of folks are arguing that a well-designed system will have a cutoff voltage of 1.1 volt. If you then extrapolate that 1.1 volt and you run into this curve, you look down here, it's argued that only this much of the charge in the battery is left over, and that looks like about 10%, they argue. And they say, well, that's what you're going to get, 10%, not the 80% that you guys are claiming. Furthermore, they're arguing that when you are trying to use this battery and boost the voltage up through a batterizer, you're probably going to end up using more charge than this 10% allows you. So not only you will not get even that 10%, you may actually get less life with a battery than you would get otherwise. Also, if you look at it, we are saying that if our claim is true and we are getting something around 80% of the charge left in the battery, the cutoff voltage needs to be somewhere around 1.3 volts. And again, it's well argued that there are very few devices that won't work down to the 1.1 volt level, and 1.3 is completely unreasonable. And so this is the reasoning that they're using to call this a scam in some cases. And at the surface, if you look at this argument in this way, I will agree that this should not work. However, the truth of the matter is that there is a lot more to this, and this is just scratching the surface. And we will go through this video and explain to you why we're missing some of the facts that will make a big difference here. This entire questioning that has been asked on how the Batteriser works reminded me of a riddle that I heard when I was going to middle school. The riddle is very simple, but it has direct implications on this issue that we're discussing. So let me describe to you the riddle, and I'm going to give you a little bit of time to think about it, and we'll come back and I'll give you the answer. The riddle goes as follows. There is a snail at the bottom of a well that is trying to get to the top of the well. In the morning time, it goes up 5 feet high up the wall, And at nighttime, it gets icy, it slides down 4 feet. The following day, it goes up 5 feet, and at nighttime, it slides down 4 feet. So effectively, it goes up 1 foot per day. The well is 30 feet deep. How many days would it take for the snail to make it to the top? Again, I'll give you a little bit of time while I'm going over and explaining how the battery works. And while I'm doing that, you can think about it. I'll come back and tell you what the answer is and what is the implications of that riddle on the questions that's being asked from us today. I want to take a few seconds and actually talk about a battery and how that works. If you look at a battery, it's a 2-terminal device. And it has its negative voltage here, and it's got this positive voltage here. It also has a open circuit voltage, which starts at about 1.6 volts or so in case of a AA battery. And if this was directly shorted here, it would turn into a power supply, but it's not. There it has this thing called the ESR, which stands for equivalent series resistance, or a resistor. And the resistor itself is a variable resistor, and its value is somewhere between 0.1 ohm to about 1 ohm based on the published papers from the battery companies. And it can actually even be higher. There are several factors that would impact that. It has to do with strong connection to the temperature. Cold temperature will make it worse, will make it larger. The battery chemistry, the type of battery, the brand of the battery, as well as what kind of a history it has, meaning how much energy was pulled out of the battery and in what shape it was pulled out, meaning how fast it was pulled out. So you will see that. Also, you will find that if there is no current going through here, what you will find here is the open circuit voltage would be here. But if you actually connect this to a load, and that load could be resistive, could be active, and what you will find is that there is a certain amount of current that's going to be drawn through the load, and that current is going to create a voltage drop across this, which would then generate this closed circuit voltage for the battery. The battery model that I showed you just now is a very, very simplistic model. We cannot really use that in a meaningful way. In order for us to fully appreciate the behavior of the battery under different loads and conditions, it would be very difficult for us to do that on an actual battery because it would take tens of hours to run. I've decided to come up with a model for the battery that is somewhat complicated. It's based on the work that was done by Stephen Hageman, and we will publish that on our website so anybody who wants to run it can run it. And the entire objective is we need to make sure this thing matches the data that's published by the battery companies, which we will see later in the conversation. So one other point that is worthy of mentioning is the fact of how much energy is left in the battery. Let's take as an example a cutoff voltage of this number. If I then take this here, it is argued by many mistakenly that this area under the curve is what's left as far as the energy is concerned. Now, mind you that let's say we're using 100 milliamp constant current, and so the 100 milliamp that we are using, if you draw that here, the area under the curve that we need to be looking at is up here. And not down here. As you notice, this works with constant current. If it was a constant resistor, you could use the area under the curve, but I can see that a lot of people are mistakenly switching them back and forth, and I wanted to make that very clear. So if you really want to know how much is left, you take this number and divide it by this number, and you can get a percentage. In this case, about 50%. But if you looked at the area under the curve, it doesn't look like anything like 50%. In yet another example that hints at the inefficiencies of the batteries and how they're designed relative to ESR, you can look at this Energizer datasheet. What it says is that if you literally take the same battery and suck 500 milliamp constant current out of it as a load, the total amount of milliamp hour energy that you're going to get out of this battery is around 1400 milliamp hour. However, if you then take the same battery and instead of drawing 500 milliamp constant out of it, you draw 100 milliamp constant out of it, you can get to 2400 milliamp hour. If you now go further and only draw 5 milliamp constant current out of this battery, the total amount of energy, the milliamp hour that you can get out of that battery total is about 3600 milliamp hours. So literally, by drawing a very low current versus a high current, you're losing about 60% of the capacity of the battery. The charge is still in there, the energy is still in there, but you cannot get it out. So let's go back to the riddle. Again, the riddle went, snail goes up the wall 5 feet in the morning, comes down 4 feet at night, and does the same thing over and over. And how many days does it take to the top of the well? The obvious answer is 30 days, because it goes up 5 feet, comes down 4 feet, so it gains 1 foot, and it will take a 30-foot deep well, it will take 30 days to come out. I would say over 90% of the people would have that answer. And it's the wrong answer. The answer is 25 days and 1 day. What would happen is, on the end of 25th day, the snail is made to the 25-foot tall. On the morning of 26, it goes up 5 feet, and it gets out of the well. It doesn't slide down anymore. So the whole concept that it would take 30 days is wrong, because we were looking at the average that it was traveling versus the instantaneous. So if the problem would have been the snail travels 1 foot a day, the answer would have been 30. However, the question wasn't, it was on the average moving 1 foot a day, but it was kind of fluctuating. And the same thing applies to the question at hand. If you look at the curves that's been given in front of us, you will find the argument of 100 milliamp constant current load is where the issue is. So after seeing the snail and the well riddle, let me draw an analogy to the problem that we have today. This is a curve of time versus voltage based on a constant current. A constant current means an average constant current out of the device. And let's say, based on the example that we had in the question, let's say there is a 100 milliamp load. Let's put that here as 100 milliamp load. What we'll show you in the lab later is that you will not find too many devices in the world that will have a very fixed constant current as the loads. That is not the case in most what you will see. What you will find is that, let's say it's even a device that's 100 milliamp, what you will find that it starts like this, it goes up to 400 milliamp, comes down to 300 milliamp, goes up, and it does this really crazy stuff all the time. That's what a normal load in a device looks like. Now, let's see what the impact of this thing is. And again, let's go back to the question raised. If it's at 1.1 volt, there is only 10% left of the energy, which again is wrong, because it's not 10%, it's the area on the disk curve. However, forgetting about that one, what will happen because of these currents that are surging? What will happen is, because of the ESR, you're going to get spikes of voltage that are going to come down. And at some point, they will run into the 1.1 volt, which is the cutoff voltage. And this is where the device stops operating. Just like the snail. Once the snail got to the top, it didn't go down anymore. The minute this glitch causes you to go below the cutoff voltage of 1.1 volt, that's where it stops. So it's not this area, or it's not this time, it's actually literally, this is the area under the curve for the energy that is still left in the battery. And we will go through this with simulations, we will go through with actual data from the device, and we will compare all that, and we'll show you how much energy is actually left in the battery. And this is really the source of the disconnect between the questions that are being asked and the answer. So we'll give you enough data to show that this is actually the case, and we'll give you measurements on those. As I explained earlier, I have come up with a SPICE model to be able to simulate the alkaline battery. What you will find here is you will see a sub-circuit alkaline. This work is based on the paper that was given by Stephen Hageman in 1990s, and I've generated a SPICE model off of it. What you will also find is that I've placed 4 different elements in this in this schematics that are 3 different batteries. That one has a 100 milliamp constant current load, one has 200 milliamp constant current load, and one of them has 500 milliamp constant current load. The purpose for this was to try to match the data sheet of the batteries. I used Duracell battery data that they have on their website, and I will show you that this is going to run and it will be matching fairly close. So let me save this. I will then go to this page and I will run the SPICE simulations. SPICE simulation is based on Eldo from Mentor Graphics. Here I will show you the graphs that you will see for 100 milliamp constant current load, 200 milliamp constant current load, as well as 500 milliamp constant current load. The reason I did all this SPICE simulation and modeling is because of the fact that most of your loads are not going to be these nice fixed numbers, and therefore this gives us a tool so we can simulate and see what actually is going on in the circuit. If you look to see if our matching is working well, I will go to 0.8 volts on 100 milliamp constant current load, and what you will find is that the amount of time it takes to discharge based on this model is around 29.8 hours. I will then take this and go to the 200 milliamp constant current load, and that gives me around 11.67 hours, which is very close to what you find on the Duracell datasheet. And then let's go to 500 milliamp constant current load, and I'm getting somewhere around 3.15 hours. So this is just to show that the model is fairly accurate and it matches the data from Duracell pretty well. One thing that I should mention, by the way, I made a mistake earlier when I said it was 29. I was looking at the wrong side. If you look at the 100 milliamp load, constant current load, and you go to 0.8 volt, you're getting around 25.9, 26 hours, which is, again, what Duracell's numbers were. I'm in the lab with one of our engineers, Chris, and he's going to go through a few of the devices that we have under test, and he's going to show us the loads, the current loads that these devices actually put out. And the intention here is to actually look at the ranges of the current loads and the fact that these are not actually constant current loads. Chris?
Okay, so the first test that I'm going to show you the setup for is this Kodak Pix Pro FZ41 AA powered point and shoot. Mm-hmm. So that I could measure the current, I had to have a wire that I could hook a current probe around, which we're using the TCP202. It's a Tektronix high bandwidth current probe. We wanted something fast enough that it could actually catch all these current events. We're also measuring the battery voltage while it's operating, so we can correlate voltage versus current in real time. I also broke out the controls, ran wires from the switches that control the camera and put them on this relay board. This relay board is programmable via the PC. We have a little program set up here where the camera will zoom out on something, and then it'll take a flash photo. Then it'll zoom back out, focus on something in the foreground, take another photo, and then we'll just be measuring the waveform as it goes. Okay. So I'll get this started and go ahead and start the test pattern. Okay, so it's already taken a flash photo. It zoomed in on something far away. First it zooms in, and that's this section right here. Then it waits a little bit, does an autofocus, takes a shot, and then it charges the capacitor.
Well, what we want to look at is look at the waveforms, look at the minimums, maximums, and even when you go up to a different state where it's going up and down, I want to look at the variations in the current and the load, and maybe even open it up, spread it out so we can actually see much better waveforms.
First of all, when it's moving the lens out to zoom in on the stuff that's far away, so...
Let's look at this lowest current. What is that?
The low current that's over here to the left?
Yeah.
Okay. So, do a cursor measurement. And right now that's at 400 milliamps.
So what is the fluctuation there? Is it going from...
Oh, the fluctuation just in that little spot?
Just in that spot.
Okay. Gotta bring that top cursor down. Okay. And we're going between, on the low end, 320 milliamps, and on the top end, 500 milliamps.
So this little bouncing is
180.
180.
Yeah.
Okay, so again, the point is it's sitting, bouncing around 180. That just looks noise. Can you kind of look at the upper one? What it went from what to what?
About 320 milliamp
Difference.
swing.
But what's the average there?
Average would be about 135 milliamps.
Okay. And so from here to up there, what's the difference in the current surge from the bottom to the top?
We're at the where it's charging the capacitor. It makes perfect sense that it's got a little 2 amp spike, because it
2 amps?
yeah, that's 2 amps.
Okay.
That's why I was startled.
Okay.
A little high. So when I'm looking at this where it's charging the capacitor, it's charging the capacitor at 1.3 amps.
Okay.
So it's pulling a pretty big load to charge that up.
And what's the voltage drop on the battery terminal at the time?
Let's see. That drop is 580 millivolts.
Oh, okay.
Yeah.
All right, so this is an example of one of the cases where massive amount of current is coming out of the as a load, and it's actually having a big glitch on the power supply itself, which is the battery for this unit. I think that makes the point that the currents are not steady, and they move all over the place.
Yeah, and even though the average current when it's not taking a photo can be down around 260
milliamp.
Yeah, 260 milliamps.
Okay.
So.
Okay. So let's go and look at another device, the choo-choo train. Chris?
Okay, so on this one, again, we've broken out the wires so that we can measure the current and measure the voltage across the battery cell.
Okay.
So get these out of the way of the scope and start it going. So, all right, I'll pause that and then turn it off. Okay, so except for the little bit where it got stopped going off the track, this is pretty much the current waveform when it's running, and also the voltage that the scope is seeing.
Yeah, just look at the voltage or the current ranges.
Okay.
It's pretty wild.
Yeah, it's all over the place. But it's just a motor. It has no filtering on it. It's going to dance all over.
Yeah.
So it goes on the low side from about 3 milliamps all the way up to, on the high side, 376 milliamps. Or no, that was 32 milliamps on the bottom.
Okay.
And 376 milliamps on the top.
And average being somewhere in the middle?
Let's see, average would be about 208 milliamps.
Okay. So this is yet another device that we have in our lab. It's a Sony speaker, Bluetooth speaker, and right now it's in the sleep mode, and Chris is going to fire it up and we can watch the current loads.
Yeah, so in the sleep state, it's got kind of an average current of about 8 milliamps, and then it has these 40 milliamp pulses when it's just talking to the computer to see if the computer's sending anything to it. So we'll play a little music for a tiny bit and see what happens on the screen. Oh. Okay, so that was a song with a lot of bass, and we can really see that. See, when the bass was kicking, we see these really tall current spikes.
So what's the big one?
Okay, the biggest current spike I see, 560 milliamps.
What's the average of the low side?
The low side.
The actual bottom side. What's the average? Somewhere in the middle.
Yeah, that's only 64.
So it's sitting at 64, and all of a sudden it's getting pulses of 500 milliamp.
Mm-hmm.
Right?
In this test, we demonstrate the useful life of batteries with handheld Gulf GPS, both with and without batterizers. The data shows that the GPS will stop functioning after 1 hour and 52 minutes, and the screen dims to dark. However, when the batterizers are used with 2 fresh batteries, then GPS will operate for 10 hours and 12 minutes.
So in this device, we are looking at a GPS made by Garmin. It's a very well-designed device. We will show you that the cutoff voltage for this device is around 1.1 volt, which is considered by a lot of the people that are having discussions as a good device. We also will look at side-by-side the device is running, as well as we've captured the last cycle before the battery died, so we can kind of zoom and look at the waveforms. Chris, you want to take it from here?
Yeah. So we're using the same current probe, this TCP202. I love this thing because it's got a great bandwidth, so I actually can catch these current events. The scope on the right has the actual the waveform of the voltage on the top and the current on the bottom as this Garmin GPS is running. So
you may want to mention that we've created a solenoid to tap this and keep it up.
Oh yeah, I thought we went over that in the other video, but just to make sure we cover that, one of our other engineers came up with this. He's just using a solenoid to pull this it's like a finger simulator, a little conductive rubber,
right.
And then that keeps the Garmin from going to sleep and turning off, because we want to do a side-by-side comparison, and if it turns off, it's not a fair comparison. We want it to actually be consistent.
Right.
So, just like earlier, I set up the cursors to give us the voltage swing. Mm-hmm. On the bottom, right here, we have 128 milliamps,
okay.
And on the top, we have 388 milliamps.
Okay.
And this is just as it's normally operating, sitting there. But after it taps, mm-hmm. there's a brief period where there's a current surge, mm-hmm. and it can go up to about 600 milliamps.
Right.
And that's where we're seeing the voltage being pulled low. And it's doing that through the whole life of the batteries. It's got that current surge that pulls the voltage low. But what happens is when it's a fresh battery, that whole waveform is translated upward, where it doesn't drop down to that 1.1 volt. But as the battery is discharged, it translates down, and you get to the point where that bottom part just kisses the 1.1 volts, and
it stops working.
Yeah, and then the device fails. This current waveform was captured from the Garmin GPS. It spends some of its time up here at a higher current, and some of its time down here at a lower current. So to get an approximate average, you split the difference and you get about 300 milliamps. This cursor reading shows 30 millivolts, and the reason that is you need to translate that into the milliamps because the current probe outputs a voltage reading. So for every 1 millivolt, you get 10 milliamps. So that's how we arrived at the 300 milliamps.
Okay, so now we're going to be looking at the last cycles of when the device actually failed.
Yeah.
So you captured on that cycle, and we actually captured some of the data around it, so we can look at what the voltages and the currents were at that time.
So the point that the device failed was right here. So I'm gonna zoom in on that so that we can really focus on it. So, yeah, and this is pretty much right after you tap the button. When our tester taps the screen to keep it awake. Shortly after that, it does some sort of acquisition, and you get this crazy waveform going.
Are we looking at that pulse?
Yeah, we're looking at that pulse. See, that pulse is
right here,
right there.
Okay.
And it's actually pretty long, having this train of these pulses. So the duration on that is, let's see, it's going to be the change in x. So that's 44 milliseconds.
Okay. So what's the current from down here,
okay,
average here to or shots?
Okay, so average down here.
Yeah. Let's look first at the average.
Okay, average down there to the middle of this.
Yeah.
Or the top of it.
Right there is fine. Go a little bit higher because of those glitches.
Okay.
Yeah.
232 milliamps.
So it's sitting at 230 milliamp.
Yeah.
And it jumps to sitting at right there.
Right there, 460.
So it jumps up 200 milliamp high.
Mm-hmm.
Then within there, you're going to get some peaks.
Yeah, and those peaks, they're like right on the top one. Right there on the top one.
Okay.
672 milliamps.
Okay, so we went from roughly 200 some milliamp to 600 some milliamp, right?
Yeah, 650.
Okay, but then
660,
once that happens,
like that.
Can you see what the glitches are for the
zoom in a little?
Voltage drop here?
Yeah. Oh, wrong time. Okay.
Yeah.
Let's see. Let's find a good one.
I want to see what voltage we actually trigger the cutoff.
Okay, that one looks like the tallest, so I should center that. So
this is kind of a surge in the current, and there's a drop in the voltage, right?
Mm-hmm.
What is the voltage?
Okay, I'll move one of the cursors up to there. Then move the other one up to the current. I can just switch channels to bounce between them. Okay, so we're still in current. So that's 664 milliamps.
Okay.
So zoomed in, we got a little more accurate on our measurement.
What's the corresponding voltage drop right there?
The correspond what is the voltage right there is 2.264.
So 2.2 over 2 batteries.
Yeah.
Is 1.11, something like that.
Yeah, 1.13.
Okay.
1.132.
So 1.1 volt.
Yeah.
Okay, good. So this effectively shows that the cutoff voltage for this device is around 1.1 volt.
Yeah.
As defined by other folks, this is a well-designed system because it cuts off at this voltage, right?
Yeah. I mean, that's what I've been hearing. So,
okay.
Also in this system, it's not a continuous load.
Right. And what's the average voltage?
Oh, okay. The average voltage before that drop, kind of in the middle of that meaty section there, 2.492 volts. So approximately 2.5.
So 1.25.
Yeah.
So effectively, this device was sitting around 1.25, and it got a glitch down to 1.1, and that's when the thing cut off.
Yeah, per cell.
Per cell.
Yeah.
Okay, good. So I think that sort of points to the fact that we were talking about different cutoffs and how steady state is not going to be the case, and this is actually the sort of the smoking gun, if you will.
Yeah.
As we discussed in the lab, the GPS unit had a cutoff voltage around 1.1 volt. And what we also noticed is that a glitch that was started at 1.25 based on the current surge dropped the 1.25 to around 1.1, and that's what triggered the demise of the GPS working with that battery. So what I'm trying to do with this model, and that's the beauty of having a SPICE model, because we have 100, 200, 500. There's very difficulty to go ahead and generate other things. But with simulation, you can pretty much do what you want to. So I've created a load that is a 300 milliamp load. Let's run that simulation and see what happens. On top of that, what I've done is I went and looked at right around 1.25 volts. I created a pulse in the current that jumps from, say, 300 milliamp to 650 milliamp, and see the impact of that on the voltage of the battery, which would drop it to around 1.1 volts. So let me go ahead and take this off and then save it. Let's go run the Eldo again. And let's now go back, look at the simulation. So what you'll find is that I have now added that pulse, which this is a 100 milliamp constant current load waveform. This is a 200 milliamp constant current waveform. This is a 500 milliamp constant current waveform. And this one is actually the 300 plus the pulse, that, the pulse. And what you will find, and if I zoom on this, let me go zoom range from 0 to, let's say, 8. And let me also go and get rid of this waveform because they are not serving a purpose anymore. And also get rid of the 500 milliamp waveform. So what we have here is the waveform for the 300 milliamp, and at the appropriate 1.25, I created a pulse on it, which shows that it actually comes down to cutoff voltage. And this is where the system dies. And what we are going to try to find out is how much of the energy is actually left in the battery. I mentioned earlier, because of the fact that we have a constant current load, the percentage of the energy that's left is not the area under this curve because it's a constant current. It's actually a box. And the ratio would be the linear ratio of how much is under where it stopped to where we would have the ending. So let me see if I can add a cursor. All right, good. Now this cursor says that I get to around 1.25-ish, somewhere around here. I did the pulse just to make a point. So let's look at that. It's around 0.538 hours. That's when the thing gets to around 1.25 and you get a pulse and it dies. So it's right around here. This is just to show from a simulation standpoint that this glitch would get you there. Now, so you got 0.538, so it's 0.54. And now let's look at the time it would take for us to actually, the battery would die at the 300 milliamp, which is about 6.94. If you divide the ratio of that time to 6.94, what you will find is around 92% of the energy still is in the battery when you throw it away. And that's a very important point. Again, this is a well-designed system by a well-known company that has a cutoff voltage of 1.1 volt, yet at the time it dies, because of a glitch gets it to 1.1, it has only used about 8% of the battery energy. And that's when we have done a side-by-side study of with and without Batteriser. With this unit, you can see that we are able to increase the battery life by 5x or more, which implies there is 80% of the juice still in there. But given that we have 92%, some of that energy actually goes to using the boost circuit and getting it up. So this is, again, in line with what we've measured and what we are seeing. So earlier I showed you a simulation model that showed for the GPS that was drawing 300 milliamps worth of current out of a battery. Based on simulation, it showed that at 1.25, where you got a glitch and that glitch hit 1.1 and the cutoff voltage and the device stopped operating, it was about 90% or a little bit over 90% of the energy was still in the battery. In order to verify that, what we've done, we've taken a Duracell battery and you're connected it to a constant 300 milliamp current load from it. The graph that you will see here is showing what the curve looks like. And there are two important things about that. If you go look at where the 1.25 volt is on that graph, it is, and you divide that over the entire period, which is 270 minutes or so, you will find that about 85% of the energy is still in the battery at the time of 1.25, which is where we saw in the lab that the device stopped operating. Now, additionally, one other important point is if you go look at a 1.1 volt, which everybody was claiming at the beginning, at a 1.1 volt, you are going to get 10-15% of energy left. In this case, when you have 300 milliamp drawn out of the battery, 1.1 actually is right in the middle, and what you will find is that about 50% of the energy is still left inside the battery at 1.1. So that also makes a big difference. So our Batteriser and the technology is not taking it, the argument is not from 10 to 90%, it's really from 50 to around 85 to 90%.
Are there any independent data that supports this claim?
We just went through a thorough analysis that showed how our technology can increase the battery life to 500% or more. We have also shown on our website that we have put a side-by-side Batteriser and without Batteriser, a well-designed system on a GPS that showed that we got more than 500% more life out of the Batteriser. We are looking at getting independent labs to test and confirm our data, and we're in the process of doing that. Relative to other types of data, let me give you a couple of data points. There is an independent study done by Dr. Zinnicker that was presented in the International Battery Recycling Conference, and that effectively showed that 10% of the batteries have almost all the charge left in them. 20% of the batteries, if you average the charge that's left in them, 93% of the charge is still in the battery. If you take the 30% of the batteries that are thrown away, 84% of the charge is still in the battery. If you look at 70% of the batteries that are thrown away and you average the charge, roughly 50% of the energy still is in the battery. So that's a very strong independent data point that points to the fact that people are missing this whole concept of Batteriser being able to add value. One other data point that is from the battery companies themselves, there is a YouTube video, Duracell official UK video, that shows that 30% of the batteries thrown away have up to 67% of the energy still in them. And that's the data from them. So we're going to get more and more data over time, but at least I can point to a couple of data points at this point. We started with a question that was asked. We then tried to come up with an answer or a structure on what's the discrepancy between the methodology of what was asked and the methodology that we use to do a much deeper dive than the simple methodology that was used to answer the question. We took it to the lab. We looked at the data on the devices to see that the loads are not constant, and the curves that we see from the battery companies are just for showing what the capacity of a battery is, and it has very limited usefulness. Using those curves, we then showed you on a device like a GPS that actually has a nice cutoff voltage of 1.1 volt. How is it that that device still has 80% of the energy left in it? Because we did a side-by-side study and showed that it actually has more than 5x life with Batteriser. We shared with you the simulation models, which then confirmed our findings from the lab. We also took some measurements from a battery, and using where the cutoff voltages were and what the average current was at that time, we could see that they all correlate and they all point to a very significant amount of energy still left in the battery, which then correlated to the life expectancy increase from the use of the Batteriser. Beyond that, I shared with you the external findings by people like Dr. Zinnicker, and even the official video from the official Duracell video that showed significant amount of charge is inside the batteries when they're thrown away. I'm hoping that by this video I've been able to explain to you why what you imagine at the first glance to be a non-workable solution is a workable solution, and I'm looking forward to your feedback. Thank you very much for your time. For the purpose of having answered all the outstanding questions, in our video we raised issue with the use of a power supply to determine the cutoff voltage of a battery-operated device. Hopefully, after seeing these videos that we've done, that question is already answered. But just in case it's not clear to some, let me be clear and explain. Let us say that we are watching a battery voltage in a device with an average current load of 100 milliamp. Now here the keyword is average current load. As the voltage of the battery gets to around 1.3 volt, in the specific case of the GPS, 1.25 volt, there is an instantaneous current load of 650 milliamp, which as we saw causes the voltage of the battery to fall below the 1.1 volt cutoff voltage. One would recognize the failure point and the amount of energy that is left in the battery at the point of the battery failure, which you can see on the curve. That, as we saw, showed something around more than 80% of the energy is still left in the battery in the case of the GPS. Now, if we take a power supply and go down the curve at 1.25 volt, when there is an instantaneous current load, the power supply keeps the voltage at 1.25 volt since it has no ESR. The device continues to function until we get to 1.1 volt on the curve, causing the wrong conclusion to be reached on the capacity of the battery when the device stops operating.